We are building the bit by bit project from the YByte Python curriculum available at www.ybyte.in. Previously, we have seen bitwise operators XOR, OR, and AND. Now we'll move forward to the next set of operators, which are the left and right shift. As before, let's first get the big picture view in place. Basically, the idea is that we, let's say, provide a single number. In this case, could be, let's say, an 8-bit number, but always provided decimals, the equivalent decimal value. And we also specify a shift value. And of course, we specify whether it's right or left. And we'll see how to do that. And output is again an integer, just like earlier. But internally, what's going on is that, we are converting, let's say, this input into its binary representation, and then we are shifting these bits either left or right. Now, let's first look at right shift. So in case of right shift, I'll be shifting these bits to the right. Whatever binary representation there is, the equivalent decimal I will put out as an answer. In fact, it turns out that this has an equivalent, let's say, arithmetic operator as well, but we'll see this in a step-by-step manner. So let's look at an example. Let's say I have right shift 43 by 1. Now this two greater than symbols implies right shift. So basically I'm saying that, look, take 43 and shift it right by 1. Now what this does is something quite interesting. Remember, the binary representation of 43 was 001 01011. When we right shift, basically we are going to move every bit to the right. We are going to put a leading 0 over here, because you can imagine that there was a 0 here as well. So we just kind of bring that back in in there. So this becomes a 0. Subsequently, every bit is moved to the right except the rightmost bit, which has nowhere to go. We just drop it. Now this is actually quite interesting. If you look at the binary representation of, say, 10101, and you end up with this, because notice 0010101, and this one gets dropped. If you look at the binary representation of this, it's in fact 21. We can actually see this quite easily. 1 plus 4, that is 5, plus 16. So remember, 1, 2, 4, 8, 16. So 16 plus 4 plus 1, and that's 21. Of course, you can also verify this using the int command, let's say, in Python. But this, I think, it's clear. Same way, if I look at, let's say, 84 and I right shift by 2. Now notice here, given that I'm right shifting by 2, the first 2 here become 0. And then subsequently, I just move every bit down, and now I'm going to drop the last 2 bits. So the binary representation of this was, in fact, 1 0. So 0101 0100. I will drop these two zeros. I will bring this 1 over here. And again, I end up with, let's say, 21. I'll just show you in Python how this plays out. So if I have, for example, let's say 43 right shift 1, notice I'm giving an integer and I'm telling how much shift to do. That is 21. If I were to do, let's say, 84 right shift 1, that's 42, and 84 right shift 2, that is 21. Now, it turns out that right shift has an interesting mathematical interpretation and hence an equivalent arithmetic operator. In fact, right shifting a number by, let's say, m is, let's say 1, 2, 3, whatever, has the effect of creating a floor division between the number and 2 to the power of m. Let's understand this in 2 steps. First of all, let's try to understand why does shifting to the right have an effect of a division. And then we will look at the fact that this is actually a floor division. To understand why it has the effect of a division, let's look at the second example here, which is 84. Remember, when I shift these two by, let's say, 2 bits, I end up with all zeros here and 1010. The drop bits were 0, so they did not influence the value. However, see this carefully. The fact that I've shifted every bit by 2 tells me that, look, I have reduced the face value of every bit by 2 to the power of 2, which is why the value of this was 4. I mean, the face value was 4, the face value is 1, the face value here was 16, here it's 4, the face value here was 64, here it's 16. And once you think through this, you realize that actually it's a division effect. Now, why floor division? Well, because, mind you, we are dropping the last bit. The last bit is, let's say, last few bits that are being dropped is a 1. It implies that we are ending up in a number which is not fully divisible by, let's say, 2 to the power of the shift. And hence, we will end up with a floor division, because effectively we are dropping this bit. we are coming down to the lowest, we are taking the floor basically from the quotient, and that's why it's a floor division. In fact, we can see this quite vividly in Python. So if I did 43, let's say right shift by 1, I end up with 21. No surprise, because 43 floor division 2 to the power of 1, which is 2, is also 21. Say if I did 84 right shift by 2, I end up with 21, because again 84 floor division 2 to the power of 2, which is 4, is indeed also 21. So really no surprise there. We kind of understand what's going on here. Now, before I wrap this up, let's do a little bit of compare and contrast between, let's say, the binary world and say the decimal world, which we are more familiar with. Think about it. If I were to shift, let's say, in decimal world, this number 20 by one bit, say one digit, I'll end up with 2, because I'll go and drop 0. I'll end up with 2, which is nothing but floor of 20 by 10. If I did the same, thing to 201, remember the last digit will get dropped, so I'll end up with 20. Once again, kind of dividing by 10. Technically speaking, division taking a floor, and hence a floor division. On the other hand, let's say if I were to do, 157 right shift by 2, I will end up with 1, because 5 and 7 will get dropped, and I'll be left with only with 1, right? Mm. Of course, I'm assuming that there's nothing like a decimal point in this. There's nothing like 1.57, 2.01, and so on. But that's okay, because remember, we are dealing only with integers over here. The important bit, however, is that same kind of logic is going on in the binary world. Just that, when I, for example, do 20 floor division shift by 1, when I do, for example, 20 right shift by 1, I end up with floor division 20 by 2, which is 10. In this case, I end up with 100. In this case, I end up with 39, because floor division 157, 2 to the power of 2. So see the similarity here. Here it was 2 to the power of m. Here it is 10 to the power of m. Other than that, the whole logic has remained exactly the same. And this should really not surprise us, because as we had seen from the very beginning, the logic of counting does not change between binary and decimal. The only thing that changes is the base. In decimal, it's 10. In binary, it is 2. Think through this. It's very, very interesting. In fact, this may look quite exotic at this point of time, but in building hardware circuits, many times we build division by 2 in, or say division by powers of 2 in exactly this way. So we have a, let's say a 16-bit number or 8-bit number. We just shift it by, say, some bits, and that gives us the effect that we are looking for. Very, very interesting, really. As always, I hope you are enjoying this journey, enjoying the process. We are trying to be quite, let's say, systematic, step by step here. We will see how all of this gets applied to the activity on LED lights, let's say, as we move forward, and that will make it all come together really nicely. Look at our website www.ybyte.in, because that is how we learn Python programming, elaborating things in detail and then building activities to illustrate our ideas. Take care. Thank you so much. Bye bye.